All right, welcome back to part 2 of this video. So for this part, we're just going to be solving the last part of this problem, which is to solve for the point loads labeled P1 and P2 on the beam. This was all the work that we had gone through in the first video, so if you missed that, go and watch that. So what we're going to do in this one is we're just going to take the stress state that we're given, this sigma is equal to that whole matrix of stresses, and we're going to go ahead and try to solve for what P1 and P2 are. So the first thing we have to do is we're going to have to figure out what types of stresses are acting at the cross section where A is. So we're going to have to move those forces to that cross section. That's the first thing I'm going to do. So I'm going to move back down to some space down here. So now we're solving for P1 and P2. So I'll just draw a small cross section here. So this is kind of like where our wall is over here. And then this is our point A, right at the top. So I've just made a section and cut, and now we need to find the internal forces that are acting at that section and cut. So I'm just going to draw them on here where you should be looking at the original diagram and seeing how they're going to be moving around, but I'm going to draw the final one. So from there, we're going to have our P2 force, which is going to be acting in this direction, so that's our P2. We'll also be having the P1 force, which is acting upwards, P1. We have some axial force right here, which is the 500, let's see up here, it is the 500 pounds, so I'm going to call that 0.5 kips. So it's 0.5 kips. And then now we need to put in the moments and torques that are caused by moving those forces to this section. So from here, we're going to have, there is a moment that is caused here by the P2 force, acting over a distance of 10. There's also a moment acting in this direction, caused by the P1 force, moving over a distance of 10. And then there is just one more, just a torque that is going in towards the beam, which is caused by the P1 force acting over a distance of 5. And so if you had trouble kind of seeing where all these come along, just look back to your 204 notes, and you should be able to see that each of these forces when being moved causes either a torque or a moment. So from here, now we can just try to say, okay, what kind of stresses is our point A experiencing? So first off, I'm just going to go ahead and draw the coordinate system that we have here, since I hadn't drawn that yet. So we have in this direction is the positive z, up in this direction is the y, and then along it is the x direction. So the first thing we should consider, so if we redraw our what our stress block for point A is, that's going to give us what we had above, which was a negative 36.5 for our sigma xx. Then we had 0 for sigma xy. Then we have a negative 9.66. Then we had that same thing, but just 9.66, and then everything else was 0. And this was in KSI. So that was what was given in the problem. So right off the back, we can see, okay, we're going to have a normal stress, so we're going to have a sigma xx. So normally with our normal stresses, that's either caused by an axial force or a bending moment. So in this case, we have both of those. So we can go ahead and say, okay, our axial force is acting towards the section cut. So that means it's in compression, so that's going to give us a negative P over A. So that's our axial stress, or our stress due to the axial force. And then we're also going to have a moment. So we have two moments in this case. We have this P2 times 10 and this P1 times 10. So if we look at our P2 times 10, it's going in the same axis as where our point A is. So that means at point A, there's not going to be any stresses due to that moment, since it's bending, that's the axis it's bending about. So that means we're only going to have stresses due to this P1 times 10. So that's going to be our bending moment we're most concerned about for our axial stress. So when we move, since this is acting at like a radius of r, we're going to have, and then if you use the right hand rule and you put your thumb in the direction of that moment and then twist, you can see that the top of that section is going to be in compression. So that's going to mean we're going to have a negative my over I. So we'll just go ahead and plug in our values for that. So we're going to have a negative 0.5 kips over our area, which is going to be pi times our radius in this case was given as 0.75 inches squared, so that's going to be our area. And then we'll also have our moment, which in this case is P1 times 10 inches, times our y, which in this case is the radius, since that's how far it is away from the centroid. So that's going to be 0.75 inches, over I, and the I for a solid circular cross section is going to be pi over 4.75, our radius to the fourth. So we can go ahead and set that equal to what we have for our normal stress, which is negative 36.5 KSI, and we can just go ahead and solve for what P1 is going to be. So P1, in this case, when you do the math, should come out to 1.2 kips. So now we just have one last stress to resolve, which is our shear stress. So we have a sigma xz stress of a negative 9.66. So there's also two things that can cause shear stresses. That's a shear force and also a torque. In this case, we also have both of those. So we're going to have our sigma xz. So if we look at our shear forces first, we have our P1 and our P2 shear forces. Our P1 force is going in the positive y direction, but since it's in the same direction as where that point is, it's like along the same axis almost, at each end of a shear force that's going in that direction, at each end it's going to be equal to 0. So where point A is where the shear force due to P1 is also equal to 0. So we don't have to consider P1, just like how we didn't have to consider this P2 times 10 moment. And now for P2, it's going to the right, so that means the maximum is along the axis that's perpendicular to P2, which happens to be where point A is located. So the maximum, so usually our equation for shear is equal to VQ over IT, but in this case, since our shear force, since our point A is located at the very maximum for a circle, we can use a special equation. So that equation is going to be 4V over 3A. So that's just for when our point that we're looking at is at our maximum. So in this case, that's what our force is going to be. Now we have to figure out if that's going to be a positive or a negative shear force. So our P2 force is going in the negative z direction, so that means that this shear force is going to be negative. So now we can look at our torque. So we only have one torque applied, so we know that we're going to have a TR over J. And now to figure out if it's positive or negative, we just look at, okay, at point A, when you have that torque applied, the stress direction has to be going that way. If you look at the torque, you put your thumb, using the right hand rule, put your thumb in the direction of the torque and then twist. If you stop at point A, that's the direction that your stress is going to be going in. So that's also in the negative z direction. So that means we're also going to have a negative torque. So now we just go ahead and plug those values in. So we know sigma xz should be a negative 9.66. And then we have that equal to a negative 4. And then our V is our P2 force over 3 times our area, which is pi over 0.75 squared. And then we have our torque, which in this case is P1 times 5 inches. And then P1, we'll just go ahead and plug that in from what we had originally solved, times our radius, which is 0.75 inches. All of that over J, and for a solid cross-section, that's equal to pi over 2.75 inches to the fourth. So now we can just go ahead and solve for P2 since that's our only unknown. And so P2 comes out to be 0.8 kips. And there you have it.